In the last video, we defined a Hamiltonian path or a Hamiltonian circuit as a path or a circuit in a graph that visits every vertex exactly once. So this graph certainly has a Hamiltonian circuit. For example, you could start at A and go all around the outside and come back again. So one example would be the circuit A, B, C, D, I, H, G, F, E, A. If it has a Hamiltonian circuit, it has the Hamiltonian path. Just sort of omit this last part here. And so notice that this particular circuit, and there's many others, but this particular example that we have here, for each one of the vertices in the graph, the degree has to be at least 2, because you have to be able to come into that vertex and leave it again. And in particular, for the 2 vertices of the graph that are degree 2, you needed to visit both of the edges that are adjacent to those 2 vertices, because in a circuit, you're always going to enter a vertex and then exit it again. Or in the starting position, you would first exit and then eventually enter it again. Oops, this is also degree 2. Okay, so if a graph has a Hamiltonian circuit, and if V is a vertex of the graph of degree 2, both edges that are incident with V, right, both that are coming out of V, must be used in any Hamiltonian circuit. Right, because it's the only way to visit and then leave that vertex is to use those 2 edges. Well, the only way to visit and leave without repeating a vertex. So that's one way to sort of help you in finding a circuit if you're given a graph. You know that if you have a vertex of degree 2, that the 2 edges will be used for a Hamilton circuit if one exists. But we have a few other different theorems that we can use in helping us to determine if a circuit exists or not. Theorem 3.2.1 is one such result. So this says that if G is a simple graph of order at least 3, and if G has the property that for every pair of non-adjacent vertices U and V, the degree of U plus the degree of V is at least n, then G has a Hamiltonian circuit. This might look a little bit familiar. The assumptions here, the sort of hypothesis part of this, looks a lot like a result that we had about whether a graph was connected or not. But in this case, we're saying if the degrees of every pair of non-adjacent vertices is at least n, the order of the graph, then we can conclude that the graph has a Hamiltonian circuit. Now, this isn't necessarily an if and only if statement. We're not saying that if it has a Hamiltonian circuit, then the reverse is true. And as an example of that, we could probably look up here, right? A and C are non-adjacent, but their degrees, when you add them together, is not at least n, the order of the graph. But for this one direction, at least, it gives us a way to check whether a particular graph has a Hamiltonian circuit or not. So we'll prove this here. In fact, we'll prove it by proving the contrapositive. Remember, the contrapositive is sort of the inverse converse, right? You swap the order of the if-then statement and negate them both. So we're going to prove that if G does not have a Hamiltonian circuit, then there must exist some pair, at least one pair of non-adjacent vertices U and V, such that the degrees of those vertices added together is less than n, the order of the graph. Okay, so if we prove the contrapositive, that's equivalent to proving the original statement. So let's assume that G is a simple graph of order at least 3 that does not have a Hamiltonian circuit. Right, assume G is simple, order n greater than or equal to 3, and that it has no Hamiltonian circuit. Okay, so what we can do is we can just sort of continue to add in edges to this graph, create a new graph, and we're going to keep on adding an edge as long as we can until we reach the point that any additional edge will form a Hamiltonian circuit. So add in new edges until you get to the point that any additional edge forms a Hamiltonian circuit. And we'll call this new graph, this graph that doesn't have a Hamiltonian circuit, but any additional edge would form a Hamiltonian circuit, we'll call that graph H. So note that G would be a subgraph of H because we started with G and just added in some new edges. It's possible that G already has the property that any additional edge forms a Hamiltonian circuit, and that's fine. G would be equal to H in that case. All right, so any additional edge would form a Hamiltonian circuit, which means there must be some pair of vertices such that adding in a new edge forms a Hamiltonian circuit. And so let's just say V1 and V2, or sorry, V1 and Vn, V1 and V1, Vn be edges, vertices of G, such that there is not an edge between them in this augmented graph H. So we're saying V1 and Vn are a pair of vertices that are not adjacent in H, but if we were to add in an extra edge between them, we would form a Hamiltonian circuit. That's what this means. And so essentially we can conclude that there is a Hamiltonian path from V1 to Vn in the graph H. Because if adding in this last edge from V1 to Vn forms a Hamiltonian circuit, then taking away that edge from V1 to Vn is going to give you a Hamiltonian path, right? Just like up here, if we had a Hamiltonian circuit, sort of ignoring the last edge gives you a Hamiltonian path. It's the same idea here. So let's say that Hamiltonian path is V1, V2 through Vn. Right, we can just say this without loss of generality. If the vertices are different names, just rename them so that it looks like this. Now this graph may have other edges coming out of each one of these vertices, but this is a graph where there is a Hamiltonian path, but there's no edge connecting V1 to Vn. Now we're going to show that the endpoints of this path, V1 and Vn, are that pair of vertices we're looking for such that the degree of one plus the degree of the other is strictly less than n. So we're going to show that the degree in H of V1 plus the degree in H of Vn is strictly less than n. Now why is that the case? Well, here's what you should notice. For any pair of vertices you choose that are interior of the path, meaning not the endpoints, for any two pair of vertices you choose that are interior and are right next to each other, so I've written an example of Vj minus 1 and Vj, it's impossible that you would have an edge from V1 to Vj and also an edge from Vj minus 1 to Vn. So what I'm saying here is that for every j where j minus 1 or Vj minus 1 and Vj are interior adjacent vertices of this path. So for every j, it would have to be between n minus 1 and 3, right? So that we start with V3, V2. For every pair of vertices of this form, there is at most one of the two edges, either V1 Vj or Vj minus 1 Vn in the graph H. Maybe there's neither, but there can't be both. So why is this true? Why can there not be both of the edges of this form? Well, if there was, then we would have a Hamiltonian path as follows. If there was both an edge from V1 to Vj and Vj minus 1 to Vn for some n, then this would give us a Hamiltonian path already. In particular, you could follow this first edge from V1 to Vj, follow the remainder of the path to get down to Vn, come back around to Vj minus 1, and then go back to the beginning. There would be a Hamiltonian circuit already in your graph, right? If both edges were present, there would be a Hamiltonian circuit, sorry, there would be a Hamiltonian circuit already, namely V1 to Vj minus, V1 to Vj, then Vj plus 1 all the way to Vn, then from Vn to Vj minus 1, and then go backwards until we get to V1. Okay. And so this is, right, this is a contradiction because we define H to not have any Hamiltonian circuits, right? So this isn't possible. So we know that for every pair of vertices inside this path, you either get this edge here, or this edge here, or you get neither. You cannot have both. And so for every pair of vertices on the interior here, we have at most one edge connecting that pair to one of the endpoints. So for every pair of vertices of the form Vj minus 1 Vj, where j is between 3 and n minus 1, there is at most one edge connecting one of these vertices to an endpoint. An endpoint meaning V1 or Vn. And so altogether, if we want to find the degree of V1 plus the degree of Vn, well, this is all the vertices in the graph right here, if it's a Hamiltonian path. So to count them all up, well, we have at most one edge for every pair. Well, how many pairs are there? You have one pair for V2, V3, one pair for V3, V4, all the way up to one pair for Vn minus 2, Vn minus 1, which gives us a total of, this is accounting for at most n minus 3 edges. All right, now we do have two extra edges here, namely V1, V2, and Vn minus 1, Vn, but that means that in total, the degree of V, make sure we can read this, there it is. The degree of V1 plus the degree of Vn is less than or equal to n minus 3 plus 2, or n minus 1. Okay, which in particular means it is strictly less than n. Right, this is what we were trying to prove. Oh, almost. Right, this is the degree in H. We're trying to prove this for the degree in G. But remember that G is a subgraph of H. So H might have extra edges that G didn't have, but G couldn't have any more edges than H has. Right, so these degrees couldn't be any smaller than the degrees in G. And so this, just sort of by the definition of G and H, this degree is less than or equal to the degree of V1 in G plus the degree of Vn in G. Okay, so this is what we were trying to show. This is a contrapositive, that the sum of the degrees in G is less than or equal to n, or strictly less than n, I should say, strictly less than n. So this proves a contrapositive, which proves the original statement as well. All right, so why is this helpful to us? Well, I mean, it gives us sort of one way of trying to determine whether a graph has a Hamiltonian circuit or not, or at least it gives us a way of ruling it out. If this is not the case, if there is a pair of vertices such that the degree is less than n, then we're not sure, right? We don't know for sure whether it has a Hamiltonian circuit or not. But if this is true, if every pair of non-adjacent vertices has this property, then you know that it has a Hamiltonian circuit. And it'd be nice if we had a theorem like the Euler circuit theorem to determine whether a graph has a Hamiltonian path or circuit, but it just doesn't exist. And in general, trying to determine whether a graph has a Hamiltonian path or circuit is a hard computational problem for a very big graph. For us, we're looking at small graphs and it's not too hard to do. Now, a nice corollary to this is if G is a simple graph of order n, and if the degree of every vertex, the degree of every vertex of the graph is at least n over 2, greater than or equal to n over 2, then G has to have a Hamiltonian circuit, and that follows easily from the last theorem. Now we have one more thing to talk about in the vein of Hamiltonian circuits, which is something called the traveling salesman problem. And we had a problem in the warm-up that was similar to this, but this is a little bit more specific, because in this case we don't just want to find a Hamiltonian path or circuit, we want to find the cheapest such path. So imagine a salesman has to travel from one place to another, and they want to do it in the cheapest way possible, and there's a certain cost associated with getting from one place to another. This is an example here of a graph. Each of these vertices is representing some location, and the edges with numbers attached to them are telling you the cost of traveling from one place to another. The traveling salesman problem asks, what's the cheapest way for a salesman to visit every vertex in the graph and potentially return to the starting position, depending on the actual question here. And again, this is not an easy problem to do. Computationally, there's no great algorithm that we know of that automatically will find you the cheapest path. For us, it's usually guess and check. So if we wanted to guess and check with this example here, they didn't give us really any specific rules here saying that the salesman had to start or end at any vertex. So let's just assume that they don't, have to go back to the beginning position. I would start by trying the cheapest edge possible, right? The cheapest edge is, for some reason, it only costs 2 units, dollars, whatever it is, to travel from L to PA. So I'm going to try to include that. The next cheapest, I believe, would be 13 from T to PE. And the next cheapest after that is 21, is the cost from MC to NY. All right, now I need to find some kind of a Hamiltonian path here, which means I need to connect these little segments to each other in some kind of a way. I don't necessarily know the cheapest way to do it right off the bat, but the next cheapest edge would be 35, and then after that would be 36. And you sort of have to think ahead and say, if I add in this 35 here, I'm not going to be able to add in 36 because it would form a triangle, and a triangle is not going to work inside of a Hamiltonian path. And so, well, this is where the guess and check comes in. If we were to include this edge for 35, the last thing that I would need to do is connect this segment over here to this segment here. And the cheapest way to do that, let's see, we've got a 60, a 70, a 68, a 61, a 51, a 78, 68, and a 51. It's probably to include either this one, the 51, or this one, the 51. Let's maybe do this. Right, this will give you a nice path from T to PE to PA to L to NY to MC. And that's probably the cheapest path, but it's worth thinking through how that would change if you had chosen this one instead. Now the other thing that you'd want to think about is, what if we had to return to the starting position? Because in that case, the only place that I would have left to do is to return back to T from MC, which would require us to take this last edge of 70. Is there a cheaper way to do it if we had made a different choice somewhere along the line? Would it have been cheaper in the long run? And again, it's not an easy question. There's no perfect, guaranteed cheapest algorithm. But this is sort of one of the things that we study in graph theory is how do we find the most reliable, cost-efficient way to solve this traveling salesman problem. So it's something to think about, and you can play around with this graph and see if you can find any better way.